Hey everyone, welcome back to Instrumentation Lectures. In the previous two videos, we were discussing about measurement of low resistances and we learned about ammeter voltmeter method and potentiometer method. So here in this lecture, we will discuss about the remaining method, which is Kelvin double bridge method. So here is the course outline for this lecture. First, we will learn about Wheatstone Bridge, which is a necessary prerequisite. Then we will study about Kelvin Bridge, which is necessary to understand Kelvin double bridge. So let's start our lecture. Let's start the lecture with a quick glance on what is Wheatstone Bridge. The Wheatstone Bridge circuit is nothing more than two simple series parallel arrangement of resistances connected between a voltage supply terminal and ground, producing zero voltage difference between the two parallel branches when balanced. So, a Wheatstone Bridge circuit has two input terminals and two output terminals consisting of four resistors configured in a diamond-like arrangement. Here, one of the resistances is unknown, and by adjusting the other resistances, we can find the unknown resistance. Let's see how. For that, let us take the current through this branch as I1, this branch as I2, through this branch as I3, this branch as I4, and current through the galvanometer as Ig. Now using Kirchhoff's first law, we can write current at junction A as current at junction A as I1 equal to I3 plus Ig. Therefore, I1 equal to I3 plus Ig. And I am naming this equation as equation number 1. Similarly, current at junction C is given as current at junction C can be written as I4 equal to Ig plus I2. Therefore, I4 equal to I2 plus Ig. And this is equation 2. Okay, now using Kirchhoff's second law, the voltage in the loop ACDA can be written as, that is loop ACDA can be written as I1 into R1 plus Ig into Rg, where Rg is the resistance of this galvanometer, minus I2 R2, and this is equal to 0. Let's name this as equation number 3. Similarly, the voltage in the loop ABCA can be written as I3 into R3 minus I4 into Rx minus Ig into Rg, and this is equal to 0, and let us name it as equation number 4. Now remember that at balance position, the voltage between point A and point C is 0. Hence, the current Ig is 0. So, substituting Ig equal to 0 in equation 1 gives us, or equation 1 therefore transforms to I1 equal to I3, and let's name it as equation 5. Similarly, equation 2 transforms to I4 equal to I2 because Ig is again 0, and let's name it as equation number 6. Similarly, we can write equation 3 as I1 R1 equal to I2 R2 because this term is 0, and this is equation number 7, and equation 4 transforms to I3 R3 equal to I4 Rx because this term is 0, and this is equation number 8. Now equation 8 by equation 7 gives us I3 R3 by I1 R1 equal to I4 Rx by I2 R2. But using equation 5 we know that I1 equal to I3. Therefore we can cancel out this I1 and I3, and similarly I4 is equal to I2. Therefore, this I4 and I2 cancel out. This gives us Rx equal to R3 by R1 into R2. So this is the equation for finding the unknown resistance Rx. Now this Wheatstone bridge itself is very accurate, but it has a drawback. The drawback is that contact resistances and resistances of leads come into picture here, and as we have already discussed, these are undesirable resistances while measuring low valued resistance. So Wheatstone bridge was modified to form Kelvin bridge. Here let R represents the unknown resistance and S represents the standard resistance. Also, this small r represents the resistance of the lead connecting unknown resistance to standard resistance. Now, initially, let us assume that the galvanometer is connected to point M. Then, the lead resistance small r is added to unknown resistance capital R. Therefore, if we write the equation for balanced bridge, we get R measured equal to R plus small r unknown resistance plus lead resistance equal to Q by P into S. So the measured value is unknown resistance plus lead resistance. So as you can see, the measured value will be greater than true value of unknown resistance R. Therefore, in this case, R measured is greater than true value of R. Now, consider the case where the galvanometer is connected to point N. In this case, the lead resistance small r is added to the standard resistance S. So the correct balanced equation is R equal to Q by P into S plus small r. But remember that we do not know the value of lead resistance small r, and the person who performs the experiment is ignorant of it. So he or she will calculate R as R measured equal to Q by P into S. That is, since the person who is performing the experiment is ignorant of lead resistance and don't know its value, while calculating, the small r is not added to S. So you can see that in this case, the measured value of R is less than the actual value of R. Therefore, here R measured is less than the actual value of R. Okay, so we have seen the extreme cases of connecting the galvanometer to point M and point N. Now let's connect it to some intermediate point C. This point C is chosen such a way that it divides the lead resistance R into R1 and R2 in such a way that R1 plus R2 is equal to R and R1 by R2 is equal to P by Q. If this condition is met, then the presence of lead resistance R does not cause any error. Let's see how. So R1 is added to standard resistance S and R2 is added to unknown resistance capital R. Therefore, using balanced equation we have R plus R2 equal to Q by P into S plus R1. Let's name this as equation number 1. Also we have R1 by R2 is equal to P by Q. If we add 1 on both sides of this equation, it becomes R1 by R2 plus 1 is equal to P by Q plus 1, which gives us R1 plus R2 by R2 equal to P plus Q by Q. Now we know that R1 plus R2 is equal to R. Therefore, we can replace this R1 by R2 by R. So we have R by R2 is equal to P plus Q by Q, or if we rearrange this, we get R2 is equal to Q by P plus Q into R. And let's name it as equation number 2. Now we will again write this ratio but in inverted form, that is R2 by R1 equal to Q by P. And just like before, we will add 1 on both sides. Therefore, we have R2 by R1 plus 1 equal to Q by P plus 1, which gives us R2 plus R1 by R1 equal to Q plus P by P. And we know that R2 plus R1 is equal to small r. Therefore, we have small r by R1 equal to Q plus P by P. And this on rearranging gives us R1 equal to P by P plus Q into R. Let's name it as equation number 3. Now plugging in equation 2 and equation 3 in equation 1 gives us, that is equation 2 and equation 3 in equation 1 gives us capital R plus R2, and R2 is Q by P plus Q into small r. Therefore, Q by P plus Q into small r equal to Q by P into S plus R1, and R1 is P by P plus Q into R. Therefore, S plus P by P plus Q into R. Solving this, we have PR plus QR plus Q into small r by P plus Q equal to Q by P into PS plus QS plus P into small r by P plus Q. Now this P plus Q is common on both sides, therefore we can cancel them out. And also bringing this P to this side, we get P square R plus PQR plus PQ into small r equal to QSP plus Q square S plus QP into small r. Here we can cancel out these two terms because they are the same. And taking PR common on the LHS, we get PR into P plus Q equal to, similarly taking QS common on the RHS, we have QS into P plus Q, and we can cancel out this P plus Qs, which leaves us with PR equal to QS, or unknown resistance R is equal to Q by P into S. Thus we can conclude that by making the galvanometer connection at C, the resistance of the lead does not affect the results. However, practically it is not an easy task to determine the correct point C such that R1 by R2 equal to P by Q. To mitigate this issue, the Kelvin bridge is modified to form Kelvin double bridge. Here, two actual resistances of the correct ratio is connected between points M and N, and the galvanometer is connected to the junction of these resistors. Now, this Kelvin double bridge is specifically designed to measure low resistances that are constructed as 4-terminal resistors. Also, note that here we have two sets of ratio arms, that is, this arm with resistances capital P and capital Q, and this arm with resistances small p and small q. It is due to this second set of ratio arm, this circuit is named as Kelvin double bridge. Okay. Also as before, here R is the unknown resistance, S is the standard resistance, and small r is the lead resistance. Now a very important thing to keep in mind is that small p and small q are chosen in such a way that small p by small q is equal to capital P by capital Q. That is the ratio of these set of resistances. Okay. This is very important. Now, before evaluating the circuit, I am redrawing the circuit like this. If you check, both these circuits are equivalent. Only thing is that it is drawn differently. Okay. Now let's proceed to evaluate the circuit. So let me name this point as A, this as B, this as C, and this as D. Under balanced conditions, there is no current through this galvanometer. This means that the potential at point D is equal to potential at point C. So the voltage drop between points A and D is equal to voltage drop between points A and C. So we can write EAD is equal to EAMC, and let us name this as equation number 1. Now this is potential EAB. So using voltage division rule we can write EAD equal to EAB into P by P plus Q, right? And let us name it as equation number 2. Now let us find the value of EAB. If you see, this is also potential EAB because point A is this and point B is this. And let I be the current through resistor S. The same current will flow through resistance R also. So the current through the unknown resistor is also I. So EAB can be written as I into S plus I into unknown resistance R plus I into parallel combination of P plus Q and R. Therefore, P plus Q parallel to R. So this can be written as, taking I common, S plus R plus small p plus small q into R by small p plus small q plus R. And let us name it as equation number 3. Now equation number 3 in equation 2 gives us EAD equal to I into S plus R plus P plus Q into R by small p plus small q plus small r into capital P by capital P plus capital Q, and let us name it as equation number 4. Now let us calculate the value of EAMC. Therefore, EAMC is equal to EAM plus EMC. Therefore, EMC, and EAM is given by I into S, and EMC is given by, if current through this branch is IMC, we have IMC into small p, and we know that the current through this branch is I and current through this resistor is also I. So using current division rule we can write IMC is equal to R by P plus Q plus R into I, and substituting this IMC over here we get IS plus I into RP by P plus Q plus R, and let us take I common. So EAMC is equal to I into S plus RP by P plus Q plus R. Note that this P and this Q are small letters only, okay? And let us name it as equation number 5. Now using equation 5 and equation 4 in equation 1 gives us, that is equation 4, equation 5 in equation 1 gives us capital P by capital P plus capital Q into I into capital S plus capital R plus small p plus small q into small r by small p plus small q plus small r is equal to I into capital S plus small p into small r by small p plus small q plus small r. So I is common in both LHS and RHS, therefore we can cancel them. And also bringing this p by p plus q to this side, this equation becomes S plus r plus small p plus small q into small r by small p plus small q plus small r is equal to capital P plus capital Q by capital P into capital S plus small p into small r by small p plus small q plus small r. And this becomes S plus r plus small p plus small q into r by small p plus small q plus small r equal to 1 plus q by p into S plus small p into small r by small p plus small q plus small r. And this becomes S plus pr by small p plus small q plus small r, these are also small letters, plus q by p into S plus capital Q by capital P into small pr by small p plus small q plus small r. Okay, and we have S common on both sides, so we can cancel them out, and the equation becomes capital R is equal to capital Q into capital S by capital P plus capital Q by capital P into small pr by small p plus small q plus small r plus small p into small r minus small p into small r minus small q into small r by small p plus small q plus small r. And these two cancel out, and this leaves us with q into S by capital P plus capital Q by capital P into small p into small r by small p plus small q plus small r minus small q into small r by small p plus small q plus small r. So if we take out pr by p plus q plus r from this term, we get qs by p plus pr by small p plus small q plus small r into q by p minus small q by small p. And in the beginning we said that small p by small q is equal to capital P by capital Q. Therefore, this entire term becomes 0. This leaves us with capital R is equal to capital Q by capital P into capital S. So you can see that the lead resistance small r is eliminated from the balance equation, and its presence does not affect the measurement result. Also, you can see that this equation is same as for the functionally equivalent Wheatstone bridge. That's all for this lecture. If you have any doubt, feel free to ask them in the comments so that either me or some other viewer can help you. Also, if you found the lecture useful, please like the video and also support us by subscribing to the channel. In the next video, we will discuss about measurement of medium resistances. Thanks for watching and have a nice day.